let me get started. So again, one more talk from IISc, and maybe I have to justify my existence here by showing you some moire, but that will come at the end. So today I'll be talking to you about indium selenide. Essentially, it's a 2D ferroelectric material, and probably since I'm talking about this talk in front of the 2D community for the first time in such large audience, probably I'll motivate you with about some of the mechanical properties that are otherwise not considered so much, right? So, and this is all the microscopy. This is a collaboration between our own group, Digvijay's group at SENSE in IISc, UPenn, Ritesh's group at UPenn, and Rohan does some calculations. I'm not going to show you any calculations. Okay, and most of the microscopy, in situ microscopy, electron microscopy work was done by Shubham, but you have Binoy also, who gave a talk yesterday, who is sitting here, who did a lot of these piezo measurements. All right, so indium selenide. My existence here is first defined by these van der Waals layers that exist, right? So I take a 3R phase of indium selenide. First of all, it exists in several polymorphs, right? And I come from an oxide community, so first when I saw this 1T, 2H, 3R, it was sort of bamboozling for me. So we understand it in terms of symmetry. So 1T is so there is a repetition of the unit cell after every a quintuple layer of indium selenide, right? So this is the quintuple layer. This is selenium. This is indium. This is selenium. This is indium. This is selenium. So this quintuple layer repeats after every van der Waals gap. And 1T is so I have a trigonal symmetry, but this repeats after every one unit cell or one layer, van der Waals layer. 2H, you have a repetition after every two unit cells. So, and with one van der Waals gap in between. 3R, again, it's a rhombohedral symmetry, right? You have a threefold axis here with so two van der Waals layers in between, or it's a three layer that repeats as a unit cell. Okay, and so you can take a 3R from so you can just buy it off HQ graphene, and then you see that you do a cross sectional imaging, you do see that the structure is indeed this. Now, so this is the polar 2H phase. Now, we have what are called alpha phases, right? So alpha are what are called the polar phases. So there is some polarity here, right? So if I look at the intra-layer stacking, that differs from the alpha to beta phase, right? And so this is the polar 2H phase where you have the zigzag sort of arrangement. So again, hexagonal arrangement. If I look at these sort of structures in the plan view, this is the cross-sectional view where you see these nice van der Waals layers. But if you see this in the plan view, you have a unit cell that is also separable, right? So for example, if I look at the T phase has, this is not very clear here, but the T phase has larger atoms sitting here and smaller atoms sitting at the corners of the unit cell. The 2H phase has a reversal of contrast. So using this sort of contrast, just looking at the atomic contrast, I'm going to distinguish between these phases, right, moving forward. There is the story of beta phases, right? So now I have different symmetries of alpha phase. All of them are polar. They have a polar point group, right? So they are, they can host a polarization. Then you have these beta phases, as you can see, so if I heat this alpha phase to high enough temperatures here, we heat it up to 320 degrees Celsius and image it, you get a beta phase. There is a change in symmetry. You can see that there is an indium and selenium sitting right on the top of each other. Here they are not sitting on the top of each other. I get back this mirror plane and I kill the polarization, right? So this is the ferroelectric to, or a polar to a paraelectric phase transition that happens, and it's reversible. Okay. Now there are so many other phases. People, if they don't understand which phase it is, they call it a beta prime phase. And so this is one such example where they see some in-plane antipolar nature, right? So although so we also see similar patterns in materials in flakes that we just heat and cool down quite fast. You freeze it into what is called a beta prime phase. Beta prime phase has some structure in plane. You can see these bands, but we have a different interpretation than what they have. We see that these bands actually come because of some indium vacancies that order themselves, right? So this is a material that is self-doped, with indium vacancies, and so you have this vacancy ordering that comes up as these bands. Okay, so these are all. I'm just discussing the structural features so that as we move along, we try to follow these structural features and see what happens once you start applying electric bias and things like that. All right, so the 1T phase, this is the beta prime 1T phases that we grow with what is called the VLS process. These are nanowires. They show these nice band-like contrast, which are coming from indium vacancy, contrast. And if we map the polarizations of this, right? So the in-plane polarization, we don't have this antipolar ordering. Rather, so it's just in one direction. Okay. Now you can go through some kind of symmetry analysis, and then you can come up with the fact that so there is a so these things, although are supposed to have a threefold axis, they don't have a threefold axis, they rather have a mirror plane here. And so you can attribute the space group of this to be PM just by looking at some seabed analysis. The reason why I'm delving so much into the symmetry of this is we have another class of materials, lead-based materials with same symmetry, where the polarization can be anywhere in this mirror plane, right? And that gives, and that is the reason for them being large piezoelectric materials, or they have large piezoelectric coefficients, right? So this looks like a duck, barks like a duck. Let's see if it is a duck. Okay, so we wanted to, and so you have, so this is in the T phase, you have a polarization pattern, but in the 2H phase, you also have more interesting physics. You have these dipolar waves and other things that are forming, and so there is very interesting physics here that happens because of some soft, Mexican hat potentials that exist in this system. I'm not going into details of it, right? So you can look at the vorticity. People doing topology can get interested in these sort of structures. Okay, but so let's get back to measuring piezoelectricity, right? So because that's something I want to see if this behaves like a lead-based material, right? So the experiment that we do is we apply bias out of plane, right? So these are the van der Waals layers. We apply bias out of plane. We actually measure. This is the PFM. We measure that you can switch the polarization from up to down, right? So that's what this hysteresis is saying. You can also do what are called the PE loops, right? So this is on an overall global device, right? So you can make these devices and measure top down, right? So with HBN and graphene, the standard things that 2D people do, and then you can measure these PE loops, and these PE loops are in this material, these are measured for the first time. And so since I have a top down configuration, I can measure what is called the D33, which is I apply an electric field in third direction and I get a strain in the same direction, right? It's not that large. It's about 30 picometer per volt. I can find ton of ferroelectric materials that have larger D33 than this. Okay. All right. But the interesting thing is it's a van der Waals material. So so if I apply an electric field in plane, what is going to happen? Right? So out of plane is sort of boring. It's just ferroelectric switching. But if I apply an electric field in plane, what is happening? And that's what Akshay has been alluding to. You can have layer sliding and things like that, right? So first, let's do the macroscopic property analysis, right? So you have this piezoelectric tensor. This is the talk that Binoy gave yesterday. So I'll just skim through the details. So D33 is a coefficient that we measured, but then the question is, can we measure this other? Can we completely quantify this tensor? And one of the coefficients we can measure based on this symmetry is D15. D15 means I apply an electric field in plane and I measure the shear strain, the X5, right? So it should shear once I apply an electric field in plane. So we made a setup for that. In fact, these are the first set of measurements that anyone can do, right? So to measure D15 in membranes and flakes. The idea is as follows, right? So you have a membrane that is clamped with these electrodes, right? So the shear strain transforms into shear stresses at the electrodes, right? So it's not allowing these things to move. And then if so if I just run a simulation of how the membrane shape should be because of applied electric field, which converts into a shear strain, so it's a profile, it's an asymmetric profile like this, right? So we can look at these asymmetric profiles and then extract out what should be the eigen shear strain, right? And that's exactly what we do, and this is the methodology that we discovered. And so you fit these to a standard, what is called an applied mechanics plate theory, and we can estimate the D15s of this, and the D15 is actually pretty huge, right? So it's 3 nanometer per volt. So I apply a small in-plane field, I have a huge shear strain in these materials, or shear stress in these materials that's going to shear them, right? So you can have layers that can slide against each other, you can have layers that can rotate against each other, and so on and so forth. If I compare it with all the other standard materials that are there in literature, and these are mostly lead-based materials, right? So they are well-known piezoelectrics. This is actually comparable or even larger than PMNPT, which is one of the well-known piezoelectric materials, right? So you have this softness because of van der Waals bonding, which just makes your layers shear with respect to each other. Okay, that was pretty neat. And then so then we apply bias, and then we see what happens. So when we apply bias, actually this is the current data in a transistor-like device setting. So the current increases, and then you have this NDR sort of region where the current suddenly decreases. Okay, we simultaneously measure the electromechanical strain, right? So this gamma 5, which is the shear strain that I'm talking about. The shear strain increases, and suddenly it starts to decrease, right? So it actually follows the profile of the current, right? So both of them are correlated. Whatever I'm seeing in the transistor data is coming from something to do with mechanical shear. That's what this means, right? And then we do a in situ Raman to actually understand what this is, and this turns out to be a phase transition, right? So I am initially at low voltages, I am in alpha phase of indium selenide, and at high, once this NDR comes up, or so this shear strain starts to go down, it transforms into an alpha plus beta prime sort of a phase, right? So again, beta prime means I don't understand it, but in literature we know that what a beta prime phase is, right? So it's a high pressure phase and so on and so forth. Okay. So this is a phase transition, and it's a completely shear induced phase transition. If I look at the underlying temperature, in this system, that's almost nothing, right? So we do have some simulations to look at the underlying temperature. That's underlying temperature rise, and that's almost nothing. Okay, so this defines my existence here. So if I can shear, right? So by applying an electric field, I mean I should be able to rotate also, interlayer rotations, right? And if you see the scale bar here, this is 100 nanometers, and then I have some ordered patterns, and these are essentially Moire patterns of a very disordered Moire pattern, right? So you can rotate, you can have rotate, you can have all these sort of structures come up where I have interlayer shear, interlayer sliding, intralayer shear, and everything that you can think of happens in this material, right? And this is the precursor to the phase transition that I just described. All right, so these are well known to be what are called martensitic phase transitions. All right, now let's do a different experiment. So this is the experiment where we made sure that there are enough heat sinks, that the temperature is not high. But now so I let go of the temperature. Let there be some Joule heating. Let all the other polymorphs also get activated, right? Now when that is done, right? So I'm applying voltage here, and I'm following the current, right? And you see that so there are some fluctuations of this current, and eventually the current just collapses, right? And this current collapse is very interesting because so typically if I take a nanowire and see that the current collapsed, so generally the nanowire would have broken or something like that. But you see it inside the TEM, you see that a chunk of this nanowire has just amorphized. It's not a crystal anymore, it has completely amorphized. Okay. So what is really happening? So we start with a nanowire which is this crystalline, and then we end up amorphizing this nanowire just by applying an in-plane electric field, right? So to understand what this is happening, we have an in situ microscopy setup where so this is the in situ electron hold. This is the in situ microscopy holder that goes into the microscope. You have all these chips that you can make. You have all these chips that you can make, using which this is a heater cum electrode. You can heat the devices inside the microscope, or you can also apply electrical bias inside the devices. So far we do 2 terminal measurements to actually see what is happening. Okay. Now let's follow this as so since it is in situ microscopy, I have to show you some videos, right? So I'm applying something happening. Yeah. So I'm applying voltage here, and I'm following the current. At some point I see these fluctuations in current, as I've discussed earlier, right? And when the fluctuations of current are happening, you have a corresponding fluctuation in the dark field microscope image, right? Now what the dark field microscope image captures is inhomogeneous strain. So I have fluctuations in inhomogeneous strain corresponding to fluctuations in the field, right? So field fluctuations correspond to strain fluctuations, again piezoelectricity in action, right? Now you can follow the same process, right? So and then so I let's say this is the marker of my crystallinity. The crystallinity sort of slowly and progressively, because of these fluctuations, it sort of disappears, and it's not a big bang amorphization event. It's crystalline to start with, and it just amorphizes as these shocks or as these fluctuations keep coming up. Okay. So what are these fluctuations, right? So I can so I have many colleagues who are single crystal growers. I can take a single crystal from them and I shear it. If I hear a sound, I keep it for my research. If I don't hear a sound, I give it back to them, right? This sound, in what is called a ferroelastic material, comes because of these sort of, so once I shear it, I have to transform from one sort of domain structure to another sort of domain structure, and that happens by forming the new domains as these needles and so on, right? And when these needles start intersecting with each other, this is like 2 tectonic plates that go and intersect each other, and that emits a seismic wave, right? So that's an earthquake at a very small dimension. Right. So essentially, this is the same as earthquake physics, just coming because of domain boundaries that are hitting against each other. So the question is, can you actually measure the statistics of this earthquake physics? We did that, right? So these are sort of the avalanches that come up, just like earthquakes, right? You can measure all these bunch of power laws. I'm sitting in front of physicists, so power laws sort of excite us. And so if I look at the earthquake physics, right? So earthquakes of higher magnitude is lower in probability. Earthquakes of lower magnitude always happens. It's exactly the same sort of power laws that you see in earthquakes, and so this is the physics of Barkhausen's noise or earthquake physics. But this is known in ferroelectrics, right? What is unknown is, so I have this now. If I take a 3D material and I create these earthquakes, once the shock is disappeared, the material sort of regains its structure, right? So the material sort of comes back. But I'm doing this in a 2D material, right? In a 2D material, it doesn't, right? So what happens exactly at a local level, right? So I have, as I see this at different stages, and at a local level, you can see that, so if I start atomistically imaging it, you see initially these bands were all straight and well ordered. Now I start seeing these dislocations that are forming. Now, so with more and more fluctuations, what started as a single crystalline nice material now transforms completely into a polycrystalline material, right? And so these also can be explained just as interlayer shear gives the interlayer sliding gives rise to these dislocations. And if I see this image, a more illustrative image, after a while, right? So this is the configuration I get. So if I look at this particular region, for example, D6. D6 is a region there where so there is a 1T to 2H phase transition. I can actually look at the unit cell of this and then say that D2 not D6, and it transforms from what I started as a 1T phase now transforms to a 2H phase. This 1T to 2H phase transitions, all these are stress or strain affected transitions, and that's exactly what we are seeing in action. Okay, so every such region is some kind of defects that are sort of in overlapping with each other, and I get this sort of contrast. All right. So essentially, because I can slide these layers so easily, and it's a thick material, I have various different configurations in which I can metastabilize indium selenide, right? So these are the various different configurations, and once locally I start creating these various different configurations, it's like I punch holes into the wall, and after a certain hole density, defect density, the wall would collapse, the structure of the wall would collapse. So similarly, so this gets frustrated, and locally I have an amorphization event that happens. All right, but the surprise is that we see this amorphization over a long range, right? So it's not a local event; it's a long range event, right? So what exactly happens? So when defects start intersect, they start forming an amorphous phase, right? But the defect intersection in these ferroelectric materials is also giving a shock, right? So I take this 2D material, I bang it at one region, the defects sort of so I start creating defects in other regions which are much long range, right? So essentially, I'm creating these defect intersections in other regions. They themselves are creating shocks. There is a replication of this disorder. It's a positive feedback process, and that reminds me of this nice story of Raktabija, where the goddess tries to kill the demon with her trident. That's a shock, and then so that gives a lot of blood droplets. Those are like my amorphous phase. And the idea is, from one blood droplet comes more of these demons. So ideally, this is a positive feedback process. Eventually, since it's a goddess, she tries to figure out a way to contain it. My material cannot contain it. It would rather percolate, and then I will have a long range solid state amorphization, which is just a percolation transition. All right. So why is this useful, right? Now, okay. So there is this thing called phase change memory in devices, right? So that's all that's there in your cache memories and other things. How much time do I have? Okay, I'm done. So let's say I want to kill Jon Snow. Right? So I take the example of Jon Snow because he can be brought back to life if you remember your Game of Thrones, right? So typically a phase change memory, any amorphization event happens via melting and quenching. So I have to create a liquid phase and then I have to quench it. The amount of energy you use here is, can be visualized to be something like this. But rather I want to kill Jon Snow in a very nice, low energy fashion, right? So if I take a piezoelectric Jon Snow, who is also 2D in nature, right? So I will, so then by virtue of the physics, earthquake physics that Jon Snow possesses himself, just applying a simple bias will, self-shock Jon Snow to death, right? And you can bring him back to life. How do you bring him back to life? Okay, so before that, there are some numbers here. So what is the energy density that you spend in amorphizing such a material using the shock-assisted amorphization that I described versus a melt quench amorphization? You have a clear advantage, right? So an 8 order of magnitude advantage. So I have to bring it back because if I have to use it as a memory, I need 1 and 0, right? So once it amorphizes, I should put in enough heat so that I have a glass transition. I have a glass that crystallizes above the crystallization temperature, right? So this is a heat assisted process, but the amorphization is something which is a high energy process that can be, so using the shock physics, you can lower the energy for this amorphization. All right. So this part was published in Nature. The piezoelectric part is not yet, it's floating around, right? And with that, let me conclude. So what I've shown you is there is rich polymorphism in indium selenide, and this rich polymorphism means once you start applying, any sort of stimulus, it doesn't need to be electric field, it can be light, you start transforming one of these phases to another phases. There is a lot of rich phase transition physics. One of the more controllable transition I've shown you is an alpha to beta prime phase transition. Again, a shear stress induced transition, shear stress, transduced from the electric field that you apply. But so if you let go everything, if you don't control the temperature as much, you also can have all these various configurations forming. You have the shock physics, and you can also amorphize these materials at a very low power. Okay. So with that, let me thank all the funding agencies. And more importantly, the facilities that allow us to do this sort of work. Thank you. I'll take any questions.
Thanks to the speaker, very nice stuff. And the session is open for questions.
Yeah, very nice talk. Finally, I got to see your results after many days. Anyways, so should I think? I think you mentioned this. So these phases can be considered as like everlasting. So there are these proposals that you can shine like an ultrafast laser, carry this using exactly the way that you're describing the sliding motion.
Absolutely.
Have you tried that?
We are doing it. So for example, on that, I can go back. So you remember this wavy thing, right? That del cross U that I was showing, wavy polarization. You shine even, I think, very low intensity. I'll tell you the numbers later. So that pattern sort of disappears, right? Even at very low intensity of light, and new patterns start emerging and things like that. That's at a very low intensity of light. You start increasing the intensity of light, you see phase transitions that we could measure through yields and other things. Right? Yeah.
How do you get back from the amorphous state to the crystalline?
Oh, it's just you have to send in enough current. That's a very good question, because if I have a long device, I cannot do it. I have to send in enough current or current density that heats up the amorphous phase back to a crystalline phase. So what we do is we actually make very short channel devices, right? So about 500 nanometers or less, and then by applying a reasonable voltage, you can send in large current, so that actually the crystallization is a more energetic process here than amorphization. Yeah, there's a question there.
How you measure the noise?
With an oscilloscope, is it? Yes. I mean, you have to measure it over 5 decades or something like that. So we apply a bias, a constant bias, and then we just keep on measuring the current.
The current noise or the sound noise?
Okay. So good question. So we measure the current noise first. All this data that I showed is with the current noise, but you can simultaneously do a sound noise, in the sense that whenever there is a shock, so we measure the out of plane displacement, right? So this is in real time, so you can actually measure the out of plane displacement using this laser Doppler vibrometry. So it's a interferometry based technique. I mean, okay, Doppler vibrometry based technique, but we use it in the interferometry mode, right? So if there is some change in the shape, that gets captured as a phase difference, and so you can calculate the displacement based on that. Yeah.
So you're saying long device, or it's basically narrow device you need? Because you need the current density or the
current density. But current density at a given voltage. I also want to apply.
Then you need a narrow device. Not
That is true.
long
But
will have larger R.
but I am applying a voltage, right? So I need to apply a reasonable voltage to get enough current density. So the length also should shift
Increase the field.
to increase the field, to get the same field essentially, right? So the length also should decrease. Yes.
I was thinking about this D51 mode.
Sorry.
D51 mode of the piezo, right? I mean, so you said
315.
the D15 or 5.
Okay.
15.
Okay.
So there is also current when you apply this voltage.
Oh,
which is
absolutely.
substantial. Correct.
Absolutely. So, what is the effect of current?
So the current means this is also, so this conduction mechanism is it's a through defects, or it is conducting material as it
So,
is?
this is a semiconductor, you have dopants, right. So, indium vacancies are also p-type dopants. So, it will conduct, right. So, it's like a semiconductor, it shows an activated conduction, right. But about the current, right, so that's why we have to always keep into account Joule heating, which is the other, you know. But what we see is, so if so we do have we don't measure the temperature, but we do have simulations of what the effective device temperature is, and that's about 1 degree increase beyond, so in the sort of conditions that we are using. But Joule heating also kills the piezoelectric coefficient. So if I start heating it, we see that if I'm doing this on platforms where I don't have a good heat sink, then my it's no longer 3 nanometer per volt, but it comes down to some 1 order of magnitude. Yeah.
Current is a drawback.
Yeah.
compared to conventional piezo.
Absolutely. So I want to do everything with field, but current exists because it's a semiconductor, right? So yeah. Tanmoy, you have a question? No. Someone raised a hand there. So
Yeah, so just wanted to maybe I can understand this. So you said you want to differentiate this with phase change material, but the moment you say that you go from amorphous to crystalline back to the crystalline, it's a phase change material.
it is I'm not distinguishing it with a phase change material. I'm saying the pathway towards amorphization is completely different.
Yeah, I mean that's the standard phase change material. So you have to.
No, the standard phase change material is melted and quenched.
Right.
So this is not melted and quenched. I don't have a melt quench transition. What I have rather is a shock assisted phase change. Okay, there is more nuance to that, but we can discuss it later, right? So maybe whatever I said, take it with a pinch of salt, but I'll discuss it.
Okay,
All right,
I have
thank
a
you.
question because there is 1 minute. So when you are creating these defects, it's like similar to software. So these defects
Similar to
software.
Yes, yes, yes.
So whether all these defects which are produced, they are of uniform size and uniform nature.
No, they are.
So then how you are saying that they will propagate in the?
So I'm not saying defects propagate. What I'm saying is shock creates defects in different places.
Yeah.
They may not be of the similar size. It depends on the magnitude of shocks that I have. And ideally, if you go back to this avalanche physics, the size of if I'm looking at spatial size, it should be length. It should be scale free. Ideally, I should have defects at all scales, right? But it will start amorphizing once I have a critical nucleus that is formed, critical amorphous nucleus, which would require certain density of defects, right? So it's a very non-equilibrium problem. I don't know how I can model it. Maybe there are experts here that can do it. So